Preparing for a Python questions for AI engineers interview? You've reached Candy Mentor, and this video is for you. We'll walk through 25 key questions you're likely to face. For each one, you'll see what the interviewer is testing, the core concepts you should cover, and a sample answer. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you explain the difference between a list, tuple, set, and dictionary in Python? The interviewer wants to assess your grasp of core Python data structures, mutability, lookup complexity, ordering behavior, and whether you can choose the right structure for AI data pipelines. While answering, focus on mutability, hashing, indexing, uniqueness, insertion order, and typical AI use cases such as feature lists, immutable configurations, deduplication, and label to ID mappings. A list is mutable and ordered, so I use it for batches, tokens, or feature arrays that may change. A tuple is ordered but immutable, useful for fixed coordinates or configuration keys. A set stores unique hashable values and is great for deduplication. A dictionary maps keys to values with fast average lookups, which is ideal for vocabularies, metadata, and label encoders. The key is matching structure to access pattern and mutability needs. Question 2. What is the global interpreter lock, and how does it affect Python code used in AI workloads? The interviewer is testing your understanding of Python concurrency limitations, CPU-bound versus I/O-bound execution, and practical strategies for training, preprocessing, and serving machine learning models efficiently. Make sure to cover what the GIL protects, why threads do not speed up pure Python CPU work, and when multiprocessing, native libraries, async I/O, or GPU execution help. The GIL is a lock in CPython that allows only one thread to execute Python bytecode at a time. That means threads are fine for I/O, such as API calls or streaming data, but they usually do not accelerate CPU-heavy pure Python loops. For AI workloads, I rely on NumPy, PyTorch, or TensorFlow because heavy kernels run in native code and often release the GIL. For Python-side CPU parallelism, I use multiprocessing or distributed workers. Question 3. When would you use a generator instead of returning a full list in Python? This question evaluates your ability to reason about memory efficiency, lazy evaluation, streaming data, and scalable preprocessing patterns common in large dataset and model inference pipelines. In your answer, talk about yield, lazy iteration, memory savings, one-pass consumption, back pressure, and examples such as reading large files, streaming batches, or generating training samples. I use a generator when I do not need all results in memory at once. Instead of building a huge list of examples, a generator yields one item or batch at a time. That is useful when reading large datasets, streaming logs, or preparing inference requests. The trade-off is that generators are usually one-pass and harder to inspect randomly. In AI pipelines, they help keep memory stable while feeding training or preprocessing stages continuously. Question 4. How do shallow copy and deep copy differ? And why does it matter for nested AI data structures? The interviewer wants to assess your understanding of object references, mutability, nested containers, and bugs that can arise when manipulating model configurations, annotations, or batched records. Be sure to mention reference sharing, copy.copy, copy.deepcopy, nested lists or dictionaries, performance cost, and how accidental mutation can corrupt preprocessing outputs or experiment settings. A shallow copy creates a new outer object, but keeps references to nested objects. A deep copy recursively copies the nested objects too. For example, if I shallow copy a list of dictionaries containing labels and then mutate one dictionary, the original can change unexpectedly. That is dangerous in preprocessing or experiment configuration. I use deep copy when isolation matters, but I avoid it blindly because it can be expensive for large tensors or datasets. Question 5. What is the difference between is and equals in Python? The interviewer is testing your understanding of identity versus equality, object references, comparison semantics, and subtle bugs that appear in data validation and model pipeline logic. While answering, focus on object identity, value equality, none checks, custom EQ behavior, in-turning caveats, and practical examples involving strings, lists, and configuration objects. Equals checks whether two objects are equal in value, while is checks whether they are the exact same object in memory. I use is mainly for singleton checks, especially value is none. For lists, two separate lists can have the same contents, so equals is true, but is false. In AI code, confusing the two can break validation logic, especially around optional parameters, cached objects, or custom classes that define equality. Question 6. How would you optimize a slow Python preprocessing loop before model training? This question evaluates your practical performance engineering skills, including profiling, algorithmic thinking, vectorization, batching, caching, parallelism, and selecting the right libraries for data-heavy AI workloads. Make sure to cover measuring first, identifying bottlenecks, replacing Python loops with vectorized operations, reducing I/O, batching transformations, using multiprocessing, and avoiding premature optimization. I would profile first instead of guessing, using C profiler, line profiler, or simple timing around pipeline stages. Then, I would check algorithmic complexity, remove repeated work, and push array operations into NumPy, Pandas, PyTorch, or compiled libraries. If I/O is the bottleneck, I would batch reads, cache intermediate results, or use faster formats like Parquet. For CPU-bound transformations, multiprocessing can help, but I would validate memory overhead and reproducibility. Question 7. Why is NumPy usually faster than pure Python loops for numerical AI workloads? The interviewer wants to assess your understanding of vectorization, contiguous memory, compiled operations, broadcasting, and why numerical Python libraries are foundational in machine learning systems. In your answer, talk about C-level loops, reduced interpreter overhead, SIMD-friendly memory layouts, vectorized operations, broadcasting, and when NumPy may still be limited by memory movement. NumPy is faster because the heavy work happens in optimized compiled code rather than inside the Python interpreter loop. Arrays are stored in compact, typed memory, which improves cache behavior and enables vectorized operations. For example, adding 2 million element arrays in NumPy runs a tight native loop, while Python would repeatedly box objects and dispatch operations. The practical rule is to express transformations as array operations, but still watch memory copies and intermediate arrays. Question 8. How does Python handle exceptions? And how would you design error handling in an AI inference service? The interviewer is testing your ability to use exceptions cleanly, distinguish recoverable from fatal failures, preserve debugging information, and build robust production AI services. Be sure to mention try except else finally, specific exception types, logging with context, not swallowing errors, graceful client responses, retries, and observability for failed predictions. Python uses exceptions to signal abnormal conditions, and I prefer catching specific exceptions rather than broad ones. In an inference service, I would validate inputs early, return clear client errors for bad requests, and log model or infrastructure failures with trace IDs. I use finally for cleanup, such as closing files or releasing resources. I avoid silently swallowing exceptions because failed predictions need visibility for monitoring, debugging, and model quality analysis. Question 9. What are decorators in Python, And where might you use them in ML or AI engineering? This question evaluates your knowledge of higher-order functions, wrapping behavior, reusable cross-cutting logic, and clean design patterns for experimentation, serving, and pipeline instrumentation. While answering, focus on functions as objects. Wrapper functions, functols.wraps, timing, caching, authentication, retry logic, input validation, and experiment logging use cases. A decorator is a function that takes another function and returns a modified or wrapped version of it. In ML engineering, I might use decorators to time preprocessing functions, cache expensive feature calculations, validate inputs, retry flaky network calls, or log experiment metadata. I would use functools.wraps so the original function name and docstring are preserved. Decorators are powerful when the behavior is cross-cutting and reusable, but I avoid hiding too much business logic inside them. Question 10. How do context managers work in Python, and why are they useful in data or model pipelines? The interviewer wants to assess your understanding of deterministic resource management, the with statement, cleanup guarantees, and safe handling of files, locks, database connections, and model resources. Make sure to cover enter, exit, automatic cleanup, exception handling, context lib, and examples involving dataset files, temporary directories, GPU contexts, or transaction-like operations. A context manager defines setup and cleanup around a block of code, usually through the with statement. Question 11. What is the difference between multiprocessing, multithreading, and asyncio in Python? The interviewer is testing your ability to choose the right concurrency model for CPU-bound preprocessing, I/O-bound data access, and high-throughput asynchronous model serving. In your answer, talk about separate processes, shared memory challenges, GIL limitations, threads for blocking I/O, asyncio event loops, coroutines, and matching technique to bottleneck. Multiprocessing uses separate Python processes, so it can bypass the GIL and help CPU-bound work. But data transfer can be costly. Multithreading shares memory within one process and is useful for I/O-bound tasks, though pure Python CPU code remains GIL limited. Asyncio uses a single-threaded event loop with cooperative coroutines, which is strong for many concurrent network operations. For AI systems, I choose based on the bottleneck: CPU transforms, file or API I/O, or request concurrency. Question 12. How would you handle reproducibility in Python for machine learning experiments? This question evaluates whether you understand random seeds, dependency control, data versioning, deterministic settings, configuration management, and experiment traceability in AI workflows. Be sure to mention seeding Python, NumPy, and framework RNGs, controlling package versions, recording configs, tracking data splits, hardware non-determinism, and logging metrics and artifacts. I treat reproducibility as more than setting one seed. I set seeds for random, NumPy, and the ML framework. And I record the exact configuration, code version, package versions, dataset version, and split logic. If using GPUs, I check deterministic options, but recognize some kernels remain non-deterministic or slower when forced. I also log metrics, artifacts, and model checkpoints through an experiment tracker, so another engineer can rerun the same setup. Question 13. What are type hints in Python, and do they matter if Python is dynamically typed? The interviewer wants to assess your ability to write maintainable production Python, communicate interfaces clearly, use static tooling, and reduce bugs in complex AI codebases. While answering, focus on annotations, MyPy or PyWrite, IDE support, documentation value, optional and union types, protocols, and limits, because hints are not enforced at runtime by default. Type hints document expected inputs and outputs without changing Python's dynamic nature by default. They help reviewers, IDEs, and static checkers catch mistakes before runtime. In AI code, this matters because data shapes, optional model parameters, and return types can get messy quickly. I use hints for public functions, configuration objects, and service interfaces. They are not a substitute for tests or runtime validation, but they make large Python projects easier to maintain. Question 14. How would you manage Python dependencies and environments for an AI project? This question evaluates your understanding of reproducible environments, dependency isolation, package conflicts, deployment consistency, and practical tooling used in machine learning engineering teams. Make sure to cover virtual environments, Conda or Venv, lock files, requirements management, CUDA-compatible packages, Docker, version pinning, and separating training from serving dependencies. I isolate each project in its own environment using Venv, Conda, Poetry, or UV, depending on team standards. For AI projects, I pin important versions because libraries like PyTorch, CUDA, NumPy, and transformers can have compatibility constraints. I keep a lock file or reproducible requirements file and build Docker images for deployment consistency. I also avoid putting every research dependency into production images because smaller serving environments are easier to secure and operate. Question 15. What is broadcasting in NumPy, and what bugs can it introduce? The interviewer is testing your understanding of array shape mechanics, vectorized computation, implicit dimension expansion, and debugging skills for numerical errors in model preprocessing. In your answer, talk about compatible dimensions, trailing axis rules, avoiding unnecessary copies, shape inspection, unintended expansion, and validating outputs with small examples. Broadcasting lets NumPy perform operations on arrays with different but compatible shapes by virtually expanding dimensions. For example, subtracting a feature mean of shape 10 from a batch of shape 3210 works naturally. The risk is silent shape compatibility that produces the wrong result, such as mixing row-wise and column-wise operations. I always inspect shapes, use explicit reshape when needed, and test transformations on a small example before scaling them. Question 16. How would you debug a memory leak or steadily increasing memory usage in a Python training pipeline? The interviewer wants to assess your practical debugging process for memory growth, object retention, data loader issues, GPU memory, logging artifacts, and profiling tools. Be sure to mention reproducing the issue, monitoring CPU and GPU memory separately, trace malloc, object graph, reference cycles, retaining tensors, batch accumulation, and controlled experiments. I would first confirm whether the growth is CPU memory, GPU memory, or both. Then I would reproduce it with a small run and add measurements around data loading, preprocessing, forward pass, loss storage, and logging. Common issues include appending tensors with computation graphs, keeping batch references, oversized caches, or workers not releasing data. I use tracemalloc for Python allocations and framework tools for GPU memory. Then remove components one at a time to isolate the leak. Question 17. What is the difference between mutable and immutable default arguments? And why is it a common Python interview trap? This question evaluates your understanding of function object creation, default argument evaluation time, shared mutable state, and subtle bugs in reusable Python utilities. While answering, focus on defaults being evaluated once, shared lists or dictionaries, using none as a sentinel, and implications for accumulators, caches, and request handlers. Default arguments are evaluated once when the function is defined, not each time it is called. So a function like def items underscore reuses the same list across calls, which can create surprising shared state. I avoid mutable defaults by using none, then creating a new list or dictionary inside the function. This matters in AI utilities because shared defaults can contaminate batches, cached metadata, or request-level state in hard-to-debug ways. Question 18. How would you serialize and load a trained model safely in Python? The interviewer is testing your awareness of model persistence formats, security risks, compatibility, artifact metadata, and reliable deployment practices for AI systems. Make sure to cover pickle risks, framework-specific formats, state-dict versus full object serialization, version metadata, checksums, trusted sources, and separating model weights from code. I avoid blindly loading pickled objects from untrusted sources because deserialization can execute code. For PyTorch, I prefer saving a statidict plus the model code and configuration rather than a full arbitrary object. For other frameworks, I use supported formats like saved model or safe tensors where appropriate. I also store version metadata, preprocessing configuration, dependency versions, and checksums. A model artifact is only deployable if I can recreate the exact inference path safely. Question 19. How would you design a Python data loader for a large dataset that does not fit into memory? This question evaluates your ability to build scalable ingestion pipelines, handle batching, shuffling, streaming, fault tolerance, and memory-aware preprocessing for AI training workloads. In your answer, talk about lazy loading, chunking, iterators, memory mapping, file formats, prefetching, multiprocessing workers, deterministic shuffling, and avoiding loading all records at once. I would design the loader to stream or chunk data instead of materializing everything. Depending on the data, I might use memory-mapped arrays, Parquet row groups, web dataset shards, or framework datasets with worker processes. Batching and prefetching should overlap I/O with computation, while shuffling needs care so it remains statistically useful without requiring full memory randomization. I would also make preprocessing deterministic where needed and monitor throughput so the GPU is not waiting on data. Question 20. What is the purpose of init.py and how do you structure a Python package for an AI project? The interviewer wants to assess your knowledge of Python packaging, imports, modular design, project maintainability, and how to organize production-grade AI codebases. Be sure to mention package recognition, public exports, avoiding import side effects, separating data, training, models, evaluation, serving, tests, and configuration management. Init.py marks a directory as a package and can define what the package exposes, although modern namespace packages have changed some behavior. For an AI project, I separate concerns: data ingestion, feature processing, model definitions, training loops, evaluation, serving, and utilities. I keep imports predictable and avoid heavy side effects at import time, like loading a model automatically. A clean package structure makes testing, deployment, and collaboration much easier. Question 21. How do you test Python code in an AI pipeline where outputs may be probabilistic? This question evaluates your ability to write meaningful tests for non-deterministic systems, distinguish unit from integration tests, and validate data and model behavior reliably. While answering, focus on deterministic seeds, tolerance-based assertions, shape and schema checks, golden datasets, mocking external services, statistical checks, and separating model quality tests from code tests. I test deterministic components with normal unit tests, then handle probabilistic outputs with seeds, tolerances, or statistical expectations. For example, I may assert output shape, D-type, schema, monotonic behavior, or that a metric stays within an acceptable range on a small golden dataset. I also mock external services and file systems where possible. I separate code correctness tests from model performance evaluation because a failing AUC threshold means something different from a broken preprocessing function. Question 22. What are Python data classes? And when would you use them for AI configuration? The interviewer is testing your understanding of structured configuration, boilerplate reduction, immutability options, default factories, and maintainable experiment parameter management. Make sure to cover automatic init, type annotations, default factory for mutable fields, frozen data classes, serialization considerations, and alternatives like Pydantic for runtime validation. Data classes are a concise way to define classes mainly used for storing data, with generated methods like init and repr. I use them for training or pre-processing configuration when I want explicit fields, type hints, and readable defaults. For mutable defaults, I use default factory to avoid shared state. Frozen data classes are useful when configurations should not change mid-run. If I need runtime validation from external inputs, I may choose Pydantic instead. Question 23. How would you build a simple Python API endpoint for model inference? And what would you watch out for? The interviewer wants to assess your ability to connect Python models to production services, validate inputs, handle latency, batch requests, manage resources, and expose reliable inference behavior. In your answer, talk about Fast API or Flask, loading the model once, request validation, pre-processing consistency, batching, timeouts, error handling, monitoring, and avoiding per-request model initialization. I would typically use Fast API with a typed request schema, load the model once at startup, and keep pre-processing identical to training. The endpoint should validate inputs, run inference under no-grad or inference mode when relevant, and return predictable response formats. I would watch latency, memory, batching opportunities, and error handling. A common mistake is loading the model on every request, which destroys throughput and increases failure risk under traffic. Question 24. How do you profile Python code, and how would you decide what to optimize first? This question evaluates your disciplined approach to performance optimization, use of profiling tools, bottleneck prioritization, and ability to connect technical improvements to AI system throughput. Be sure to mention measuring before optimizing. cProfile, line profiler, PySpy, memory profiler, wall clock versus CPU time, representative workloads, and optimizing high-impact bottlenecks first. I start by profiling a representative workload, not a toy path that hides the real bottleneck. cProfile gives a broad function-level view. Line Profiler helps inside hot functions, and PySpy is useful for sampling running processes. I also separate wall clock time from CPU time because I/O waits need different fixes than computation. I optimize the largest bottleneck first, then remeasure. In AI systems, the best improvement is often keeping accelerators fed, not micro-optimizing small functions. Question 25. How would you explain the role of Python in an AI system when the heavy computation often runs outside Python? The interviewer is testing your architectural understanding of Python as an orchestration layer around optimized native kernels, GPUs, data systems, APIs, and experiment workflows. While answering, focus on Python's ecosystem, its glue code role, native extensions, tensor libraries, CUDA kernels, productivity, orchestration, and the importance of knowing when Python becomes the bottleneck. Python is often the control plane for AI work. It defines data pipelines, model architecture, training loops, evaluation, APIs, and experiment management, while heavy tensor operations run in optimized C, C++, CUDA, or vendor libraries. That combination gives high productivity without giving up performance. The key is knowing where the boundary is. If Python is orchestrating large vectorized kernels, it's fine. If it's running millions of tiny loops, it becomes the bottleneck. If you are still with us, Congratulations! You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.